73s from Hallicrafters rehabs today. 73s is an old amateur radio expression dating back to sending Morse code back and forth, code wave, and it means that at a minus 73 dB or 50 microvolt signal at the antenna, you should receive an S9 on your S meter. Now, I've mentioned in previous videos that it seemed like this Hallicrafters SX-71 was maybe tracking 3 dB or so less than my other Hallicrafters radios. Here's one. Right now we're watching or listening to, alright, there's one. That's one rebuilt SX-99 that's actually showing about 10 or 15 dB units or so higher than the SX-71. And then this one was rebuilt. And this one actually is fairly close when you put it up against a test signal. 73 dB will give you pretty close to 73 dB on most of the bands. On the SX-71, it only does an S5 or 6 signal depending on what frequency you're at. And then here's the SX-100, still in the queue for restoration, but working well, and it's pretty close as well. So, alright, is it a problem with sensitivity or what? And I have been spending a lot of time studying this particular phenomenon and the S meters in general. And so we're going to have to go back to our whiteboard and take a look. So in order to figure out what was going on, I had to do some studying. And I went back to my trusty old Fundamentals of Radio book, published in 1938. Probably if you were in electrical engineering at NC State, actually I got this at a book fair probably 50 years ago, or when I was in school at the NC State, whenever that was, maybe 45 or 50 years old, whatever it is, 71, 69. And this was sitting in there, and oh boy, I can learn about my SX-71 radio. And I've had this for ever since then. It's perfect. It's absolutely, for the kind of things that I do and the kind of things that I study, it's right at my level of technology, which is not contaminated by solid state or anything modern like that, or the 21st century, none of that. So this book actually is very excellent if you were studying radio back then, which is probably a course that they had in their EE department way back when. You probably had this as a textbook. So an S meter is basically a current measuring device, and to understand how it works, we have to go back to the fundamentals of a tube itself. I wish I could write more neatly. That says voltage. But if we're taking, in the case of the SX-71 or the SX-100, the tube is a 6BA6. And to make it more, yeah, that's in the middle. To break it down very simply, we'll imagine that it's not a cylindrical tube, but it's just a series of plates. And you have first the cathode, and you have a grid, a screen, and a suppressing grid, and then the plate. It's called a pentode, I guess. And when you apply voltage to the plate, the cathode is essentially referenced to ground. This is actually 82 ohms off the ground, but it's close to the ground. When you apply 220 volts to the plate, an electrostatic charge is set up on the cathode. And the grid is usually negative voltage. In the case of the SX-71 is +2 volts, very close to negative. Then you have the screen, which is really what the cathode electrons see. They can't actually see the plate, they see the screen, which attracts them, the electrons, towards the direction of the plate, and then they pass through the screen. The suppressor grid, I'll talk about in a second, then they will pass through there as well, except for the ones that are absorbed by this, which is at ground, or the cathode voltage. That's why the voltage drops here. But then the plate, the electrons see the plate at 220 volts, and so you see the real amplification in the tube right here. And the purpose of the suppressor is when the electrons hit the plate, they hit so hard that they actually will bounce off. And what this does is actually slow down the electrons so that they can be absorbed by the plate more efficiently. When you're in a no signal state, zero state as far as the tube, it's all warmed up and running, current is flowing at its maximum. And if we look at the characteristics of a 6VA6, which I have over here, essentially this is at 0 volts, 220, so you're looking at 16 millivolts at the no signal state. Now what happens is your signal, say it's from the antenna or whatever, it comes into the grid, and it will be a carrier signal that's modulated. It's an AM signal in these sets, and so that will add or subtract to this voltage, and it's magnified by the amplification of the tube right in here towards the plate. And as more signal is applied, this becomes more negative, and this voltage drops. Mainly the voltage doesn't drop, but the current drops. Essentially the tubes are close to constant voltage, and they vary in current. So what does an S meter do? The S meter is in the plate circuit. Here's the plate bias resistor, 3300 ohms, and it's a simple current ammeter. They typically are very low. Maybe the peak is 100 milliamps or a few milliamps. So it's measuring microamps more than anything. There's a little bias resistor right here of 82 ohms, and the zero adjust is a little pot in the back that's only got like 200 to 500 ohms total in that pot. So it's a very, very simple circuit. Now, hams want to calibrate that S meter to 73 dB for an S9 signal, particularly for their transceivers. And in today's digital age, that's you essentially program every bar on a multi-bar S meter, or you have a whole circuit in there that including a pot right here as well as this pot to balance and calibrate the S meter. Now not to be undone. I should say not to be outdone. I even tried putting a little pot in there to see if I could get the S meter to calibrate a little better than it does, but it does not. So essentially, it really is, it is related to the sensitivity of the set, but there are many other factors associated with the S meter, and let me show you that. I did a plot of all those radios at 1,000 kilohertz, 1 megahertz, just to see. And the SX-71 is the blue line here. The one SX-99 that I showed you at the bottom there that was fairly close is this gray line. The one which is the yellow, which is like this, is the SX-100, and then this orange one is what I thought or considered to be an S meter that was a little bit too bouncy or light, as somebody might say, whereas an SX-71 might be a heavy or a slow moving or less moving S meter. Well, that's not right. See, the other thing about this is that these are configured so that max current is here. Max current is deflected all the way to the left. So at zero, no signal state, just like it is up in the tube, the maximum current from the cathode to the plate is at S0, or no signal. And then as a signal is applied, the grid becomes more negative, the current drops, and so you'll see a drop in the current, which is your S reading. A drop in the current is your S reading. So, in reality, the SX-71 has a more bouncy meter. It deflects all the way to zero a little faster than the others. Whereas I'm thinking I may need to do some servicing on this one because it is so unbouncy that I may have the wrong bias resistor or the wrong pot resistance or something in there, because it's significantly different than the other SX-99. Now the SX-100, it wasn't so great at 1,000, but on the other frequencies it tracked pretty well. So what I did was I did a study of the various frequencies for the SX-71. I could do this for the others, but this was really time consuming. And so what we find is that the S meter becomes a little more accurate between 7 and 14 megahertz, and even at 25 megahertz. But in the low frequencies like 1,000, it drops off. Now this line here, 7 megahertz was also pretty low. Where's that? That's the S9 right here. So, but around 11 it seems to be fairly close, as we were looking at in there. So again, trying to see if we could sort of suppress that movement a little bit with something like this pot, really it would take a lot of design work. And because what happens is that the zero adjust starts getting into the picture, and you can get a perfect adjustment at S9 equals 73 dB, but you'll be having it'll be like a watch that stopped. It's right twice a day. The zero will be at S3, or on another frequency it'll be all over the place. So you pretty much have to live with it like it is. And for, I would say, any radio, if you have the equipment to do it, and you're interested in what, you know, the signal level is, just make a table like this, and it'll give you an idea of where the S meter is in relationship to the strength of the signal coming in. And also, I should give credit to Greg, a ham whose call is W8WWV, and gave me the idea of doing these kinds of comparisons between, he was doing it for different transceivers, but it's the same thing you could do for any receivers, where you have the ability to have a calibrated source and then distribute it to more than one receiver. So the way I configure things is I start with a calibrated signal generator. In this case, we're going to go through 7 megahertz. It goes through a calibrated attenuator, and then I have a spectrum analyzer that's just simply measuring the signal as it arrives at the set. And then the signal generator through the attenuator goes to a splitter, which is very hard to see back there, which goes 4 ways, and it will go to this receiver, this one, and the SX-100. Alright. So to start out with a demonstration of how to do this for any one frequency, you just set your signal generator up, and I'm going to do one at 10 megahertz right here. Then it goes through the calibrated attenuator into a splitter behind, and then from the splitter to the 4 receivers, and off of one of those directions I have a reading here of minus 73 dB as a starting point for this particular frequency measurement. And right now you want to do some fine tuning, because I've just turned these receivers on after a day or so, and it's reading S8, so it's closest to I would say, you might say, calibration, around 10 megahertz, 11 megahertz, something like that on the SX-71. But then we look over at the SX-99, the older one, and it's a real delicate tune here. 10 dB over S9. The one below it is a little bit more than that, and then the SX-100 is also over 10 dB over S9. Then with the signal generator and the attenuator, you start marching down and marching up the attenuation. So I'm going to record this real quick. For the SX-99 at 10 megahertz, it is S8 equals 73 minus 73 dB. So to bring it down on the spectrum analyzer, we'll just knock it down. And it's never more exact. You want to just use the reading on the spectrum analyzer. So 3 dB down, dropped it to S7 like it should. And that is reading at or roughly minus 76. And then you can either tune or I should say attenuate the amplitude on the signal generator. We'll go down 1 and 2, and that's almost at, okay, that's S6, and we're reading minus 73. Okay, so that's minus 80. Then going down, we'll just knock this down a little bit. Okay, so at S5, minus 89. And this continues. I'm not going to go through all of this, but I'll show you the result in just a minute. So what I did was I plotted it out on the same graph as I did before. And of course I never make mistakes except for all the time, and I started out without zeroing the S meter. So you see all this chicken scratching over here is related to the fact that I had to go back and revise those numbers after I re-zeroed the S meter. Now there is, in the operation of the S meter, there is no inflection point. The inflection point is actually in the markings on the meter. You know, an ammeter is an ammeter. It doesn't, care. It's just more current, more deflection, less current, less deflection, and it's linear. What they do is to comply with conventions, they change the demarcation from 3 dB per S number below S9 to 10 dB per marking above S9, and that's why you get that deflection in the graph. It's not really a deflection, it's just the way there's no good way in Excel to carry this out further, but anyway, that's the way it works. So we see here then that basically the SX-71 meter deflects more for each movement of the S meter, or the more it deflects more for any given value of current that's going through to the 6BA6 tube, whereas in these others, which looks like that's showing a higher signal, that's not the case. It's just less current going to the 6SG7 tube and the SX-99, and of course the SX-100 is the 6BA6. So in short, S meters are a relative indication of strength of signal, you can make a table like this if you're really interested in knowing how much actual what the microvolt level is, for example, at the antenna, or you can use a table like the one I made to do a pretty good estimate based on whatever frequency you're on and whatever signal level you're seeing on the S meter. So as we listen to CFRX in Toronto, and a last observation about all this is that basically as I was getting down into the weeds, very close to the noise, you could tell which radios were the most sensitive, and this one is right there with this one. And I actually haven't really done a minimum detectable signal analysis on this radio yet, because I've only serviced it. I've never restored it. But in the future, I'll be doing that. And this is really this SX-71 is performing very well. And with that, I'd like to wish everyone a Merry Christmas and a Happy New Year. The next step with set of tests will be to do the gain at each of the stages to document that. And then I have some modifications for this, which will be very interesting. And we'll see that next year. This is Howard at Hallicrafters Rehabs, and Merry Christmas. Oh, by the way, as we sit here and listen to All India Radio, you can use it if you have a spare spectrum analyzer hanging around anywhere. You can use it as a pan adapter, but I would caution you to not just do it direct without having at least some kind of attenuator in line with it, especially at night times, or you can overload the spectrum analyzer pretty easily. So, but it's okay. It works pretty good. It's a little bit cumbersome, kind of a fun thing to do.